Hi, I'm Yuxin. I'm from University of Warwick, and today I'm presenting our collaboration paper with our partner in Orebro University in Sweden on multi-sensor unit on mobile robots for unsupervised gas discrimination in harsh environment. So the project we are working on is called Mobile Project. It's about robots operate in domains with restricted visibilities and hazardous environments, such as in support for fire brigades in search and rescue mission. So our aim is to enhance the cognitive abilities of the mobile robot. So we are building these novel sensing systems, including LiDAR, 3D radar, thermal camera, and gas sensing unit. Altogether, the data collected for mapping, such as navigation maps or gas distribution maps. And we're also working to integrate the whole system into prototype a commercial low visibility explorer robot. As you can see on this image, that's the actual robot we're working on. So our task in this project is the gas sensing unit. So we have to integrate a multi-gas sensor unit in order to discriminate gases and generate a gas distribution map. And the discriminate part is done by our partner in Orebro University. So there are lots of commercial sensors available on the market for gas detection, but they are not suitable for our application because of their slow responsibility and poor selectivity. And also because we're working in hazardous environments, so we have to compensate for humidity or temperature, and we have to have a robust housing to keep our sensors safe and through the whole experiment. For gas discrimination, because it's unlike laboratory conditions, we don't have any control towards humidity, flow, and temperature. And any robot movement will create like vibration or spikes in our sensor response. And also, unknown gas interference might disrupt discrimination algorithms. So all we are working on is to build a robust, high bandwidth sensor unit for unsupervised gas discrimination. So I will start talking about our sensor unit and then go to discrimination and then experiment the results. So here's a block diagram of our sensing unit. We presented our first generation sensor box last year in the same conference. And based on that, we enhanced the signal processing capabilities. We improve our sensor response time, and we reduce the physical size of the unit. With this unit, we have 3 MOX sensors, 1 NDIR sensor, 1 commercial environmental sensor, and 1 optical particle sensor. So the detail is, for the 3 MOX sensor, we have metal oxide gas sensor. These based on CMOS compatible microheaters, which is size of 1.2 millimeter and 1.2 millimeter, which is the one, I don't know how to use that one, which is the little bit that inside that. The 3 MOX are doped tin oxide, tungsten oxide, and nickel oxide respectively for CO, NO2, and VOC detection. All MOX sensors have high sensitivities of less than 10 ppm detection level and low power consumption of 76 milliwatts. The response time is less than 10 seconds compared to the commercial MOX, normally 30 seconds or even longer. We have NDIR, non-dispersive infra-red gas sensor within the unit. It has a plasmonic structured infrared emitter, which is the one showing there. So because it's plasmonic structure, so we can tune this for different gas. Like for now, we have a CO2 emitter, which is tuned for wavelengths of 4.26 micrometer. The power consumption of this whole unit is 100 milliwatts, and the response time is 30 milliseconds. The size of that is about 5 centimeters for now. All sensors are driven by high-frequency pulse width modulation. So apart from this, we have 3 commercial sensors. We have a Bosch BME280 environmental sensor for temperature, humidity, and pressure. We have a Honeywell flow rate sensor and optical particle sensor for small particle detection. We have 3 valves, 1 3-way and 2 2-way. So the 3-way can have 2 gas inlets located on 2 different heights on the robot for gas at different densities. And the 2 2-way, together with a micro pump, could isolate the system and protect the system when the temperature gets too high. The whole unit is within this steel metal box, which is size of 100 by 100 by 100 millimeter. This is 30% smaller than our last generation. And in order to do some onboard filtering, we replaced the microcontroller with TINC 3.6. So we could sample our raw data at 100 Hertz, which is stored into the onboard micro SD card, and at the same time do preliminary processing on the microcontroller. and the processed or filtered data is output to robot at 10 Hz for gas discrimination algorithm. So before we sending this unit to Orebro, we test this unit in our lab back in Warwick using a gas rig. So for Explorer robot, we want to target like toxic gas like CO and NO2. But because in Orebro we're doing gas discrimination in open environments, so we can't release any of the toxic gas. So we replace them with propanol, ethanol, and acetone. So we tried all the gas in our lab, and here's an example of the acetone result on our MOX. The top one is for tungsten oxide, the bottom one is for nickel oxide. Maximum of 200 ppm acetone is in dry air is posed at 5-minute steps at different concentration. So nickel oxide responds very well to acetone and tungsten not that much. So we could say our MOX has excellent selectivity towards acetone, and this selectivity is better than any commercial MOX sensors. The reasons behind this is because we have different chemical coatings for different MOX to target different gas. Then we brought this to Orebro to place on this robot. So on this robot, we have our units down there. We have a commercial array of commercial e-nodes, which is an array of 5 or 6 commercial sensors our partner in Orebro University use when developing their algorithms. And we have a commercial PID unit to have the actual ppm reading. So the robots drove towards the gas source individually and parked about half a meter away for 5 minutes. Gas inside the bubbler, for liquid gas inside the bubbler, and the fan is used to facilitate airflow. After 5 minutes, the robot drove towards in a clean air or baseline area so the sensor could recover. So all data are collected in using robots, and then the time series of MOX response are separated for 3 gas of 3 classes, and then assigned a ground truth label, which is normally between gas for evaluation purpose. We tested two class hypotheses. So we tested propanol versus acetone, ethanol versus acetone, and the propanol versus ethanol. Because it's unsupervised, so we don't need any training data. So performance is evaluated using an index called exact match ratio. So that is defined by number of correct prediction over number of correct total measurements. Number of total measurements. So the detailed algorithm was presented by our partner in Orebro University last year in the same conference as well. And both pre-class classification rate and overall classification rate are considered. And the result is showing. So for propanol versus acetone and ethanol versus acetone, the result is showing here. So on both of the plots, the red dot is acetone. And on this one, the green dot is propanol, and the green dot here is ethanol. So the algorithm is able to tell this data is from 2 different classes or for 2 different gas. And the overall performance ratio for propanol versus acetone is 95.91%, and for ethanol versus acetone is 89.76%. So even though we parked our robots stay stable for 5 minutes, there's still fluctuation in the sensor response. So we conclude this as a gas plumes, the effects of gas plume. And that little box over there, the blue dash one, is misclassification. Okay. And the result for propanol versus ethanol. So for the red dots is ethanol and the blue dots is propanol. So the overall performance, so we did 2 experiments. So the performance for the ratio is 95.91 for the first time and 96.56 for the second time. So the misclassification only occurred during transitional period or between gases. So to some extent, this could be neglected. And so far, we are able to discriminate 2 different classes successfully at the same time. So to conclude, we have this new and improved gas sensing unit, which has physically compact size of 30% smaller than our last generation presented last year. We have 2 gas inlets located at different heights on the robot. We improve our sensors, and we have better onboard signal processing capabilities for filtering, fast Fourier transform, or thermal modulation. Within this unit, we have 3 microheater MOX sensors, 1 plasmonic enhanced NDIR sensor, 1 particle sensor, and 1 BME280 temperature, relative humidity, and pressure sensor. The sensor unit was tested both in our laboratory setup and on a mobile robot in uncontrolled environment. in collaboration with our partner in Orebro University, we're able to do offline unsupervised gas discrimination. And the discrimination ratio for propanol versus acetone is 96% accuracy, and ethanol versus acetone at 90% accuracy, and ethanol versus propanol at 96% accuracy. For further work, so we would like to have 2 sets of mocks, because for now we only have 1 set which is target for CO and NO2, but we would like to have another set which only used for gas discrimination algorithm, so it will target propanol, ethanol, and acetone. Because of that, we are going to do customized coding for all the mock sensors to target different gas. In this experiment, we didn't use the NDIR gas result, is because the one we're putting in the unit now is for CO2. But we could easily tune that for acetone or ammonia, which we do have the emitter available, so we're going to incorporate that data into the further discrimination to have a more comprehensive result. We will also observe the gas plumes, and we would like to study the effect of gas plumes or sensor response, and possibly use that to get localization of gas source. For discrimination, we did so far is all offline discrimination. We would like to move that to online in real time and discriminate multiple classes of gas in real time. And that's the end of my presentation, and this project is fully funded by EU Horizon 2020 Small Ball project. And thank you all very much for attention. Thank you for listening.